Hello guys, welcome to Physics Grad. In this video, we are going to explore the underlying connection between symmetry in the system and the corresponding quantities that are conserved as a result of this symmetry. Okay, so let us begin. So in our previous lecture, we have already seen that. The change in the Hamiltonian, which I am going to call dou h, which is given by h of a minus k of a dash, is given by minus epsilon dg by dt. Okay, that is the total derivative. So here, as we have seen, the points a dash corresponds to the following things. So if we have a phase space eta and I define a point A here, if I look at the canonical transformation in terms of the passive interpretation, then this is going to map into another phase space psi corresponding to the point A dash. Okay, and if we look at it in the active interpretation, then the canonical transformation takes us to another point B in the same phase space eta. Okay, and such a canonical transformation, in fact this is an infinitesimal canonical transformation, will be generated by a generating function of type 2 given by summation over qi pi plus epsilon times g, and that is where this g comes from. Okay, so here the transformation which takes us from A to B is nothing but the infinitesimal canonical transformation in terms of the active interpretation, and the transformation from A to A dash is also the same infinitesimal canonical transformation but under the passive interpretation. Okay, now if you look at this equation, what you see is that if dg by dt is equal to 0, or in other words if g is conserved, this implies that h is invariant, or the Hamiltonian is invariant under a canonical transformation, okay, which is generated by the function g, which in turn is a part of f2. Okay, so this implies that there is a connection between symmetry or symmetry properties of the system and conserved quantities. And what is this connection is what we are going to see in this video. Okay, so we are going to consider first the case wherein the quantity g is not explicitly dependent on time. Okay, so this connection is easy to see for those constants of motion, I'm going to call this as constants of motion or integral of motion because our g dg by dt is equal to 0, which means it is conserved, or in other words g can be taken to be a constant of motion, and that is why I am saying this connection is easy to see for those values of, or for those constants of motion, or for those g's, okay, that don't explicitly depend on time. So this implies that dou g by dou t is equal to 0. But remember, in this expression it is the total derivative, not dou g by dou t, it is dg by dt. Okay, so this implies that our change in the Hamiltonian is going to be h of b minus h of a minus epsilon dou g by dou t. Now I got this by substituting for k of a dash as equal to h of a dash minus plus epsilon dou g by dou f by dou t, and dou f by dou t is same as dou g by dou t, and h of a dash is same as h of a, as we have seen in the previous video, and this expression is going to be equal to minus epsilon dg by dt. All of this we have derived in our previous lecture. Okay, so this in turn implies that our dou h is going to be simply equal to h of b minus h of a if there is no explicit dependence on time. Okay, and this is of course equal to minus epsilon dg by dt. Okay, so if you interpret this relation in terms of this difference, what it is saying is that this is equal to change in value of h as the system moves. So I'm going to call this moves in double quotes from point A to point B. Now when I say the system is moving, this is I'm saying it in terms of the active interpretation. It doesn't mean that the system is moving in the actual path where it is supposed to move. What it is doing is that this is a canonical transformation, not necessarily the equations of motion, but what it is saying is that if we perform such a transformation, it takes our system from one point in phase space to another point in the same phase space. Okay, and how it takes from one point to the another will depend on what this generating function is. And as we have seen in our previous lecture, if we had chosen this generating function as the Hamiltonian itself, then the resulting transformation will give us the motion along the actual path which is taken by the system following the equations of motion. But in this case, we are not choosing g as the Hamiltonian, so therefore it is nowhere related to how the system actually moves in phase space. What it is just telling us is that this particular transformation takes us from one point to another point in phase space. That's it. Okay, it doesn't mean the system is following this particular path. Okay, and we are examining what happens when, if the system is taken from this point to some other point via this particular canonical transformation, and this need not necessarily be according to the equations of motion. Okay, we are just examining. So for example, you might want to perform a particular experiment on a system at point A and perform the same experiment on the system at point B, and you want to see whether the system is going to behave differently in point A and point B. So if the point A and B are related by this kind of a canonical transformation, and if G is conserved, what it says is that the Hamiltonian of the system at point A and point B is going to be the same. Okay, if the quantity G is conserved, or in other terms, if this is 0. Okay, so let us write those things down first. So note that unless G is equal to H, this motion that I have talked about here is not along the actual path. Okay, this is an abstract motion in terms of the active interpretation, as I told you when I gave you the example about conducting the experiments at two different points and examining whether the system behaves the same way or not. Okay, so this motion is just a way to interpret this canonical transformation. So this interpretation is according to the active interpretation. Okay, so before we begin, since we are finding the connection between symmetry and conservation, we already know what do we mean by conservation. Conservation means the value shouldn't change as time progresses. But what do we exactly mean by symmetry? And we are going to learn what this symmetry means, at least intuitively, before we further proceed to explore the connection between symmetry and conservation. So let us see what do we mean by symmetry. So we are going to understand what symmetry means in terms of some easy examples. So I'm going to begin with an example of a sphere which is uniform in mass and made of a single material. Okay, so we have a particular sphere like this, and let's say that this is the point from which we observe the sphere. Okay, and let's say that we have observed the sphere at time t naught. Okay, so observing at time t naught. Okay, now I want you to imagine the following experiment. So first, close your eyes at t naught. Okay, and then ask someone to rotate the sphere about any axis that is passing through the center of mass. Okay, so let this take some time t, that is, to rotate the system, let the person who is rotating the system take some time t to do it. Okay, so now open your eyes at t naught plus t, that is after the person has rotated it. Okay, now I ask you the following question: can you tell if the sphere was rotated or not? Okay, if the sphere was rotated or not. Okay, so provided there is no special marking in the sphere or no reference of any sort, if the sphere is made of the single material of the same color and uniform mass, then there is no way of telling whether, after we open our eyes, whether the person has indeed rotated this sphere about an axis passing through the center of mass, say something like this, or whether he has not rotated it. There is no way of knowing unless we mark every point which is making up the sphere. But here, of course, we have not marked them or named them, so we will not be able to distinguish whether the sphere has been rotated or not. Okay, so when this happens, so the answer is no, because under the operation of rotation, so rotation is some kind of a transformation that is happening on the system. Okay, so because under the operation of rotation about an axis through the center of mass, the sphere is said to be symmetric. The sphere is said to be symmetric. Okay, so I shouldn't say because, this implies. Okay, so since we cannot observe any change in the sphere when we rotate the sphere about an axis passing through the center of mass, we say that this operation of rotation has not affected the sphere in any manner, and we say that the sphere is symmetric under this operation. Okay, so let us consider another such example, and let us consider a cylinder in this case. So example, a cylinder. So if you take a cylinder which looks something like this, let's say, we see that the cylinder remains the same only if we rotate it about an axis passing through the center which looks like this. Okay, so this is symmetric. We say that this is symmetric with respect to rotation about this axis. Okay, so by now you should be having an intuitive feeling to what we mean when we say that a system is symmetric under a particular transformation. So here in this case, if you again perform the same experiment, that is, you close your eyes and let someone rotate this cylinder about this axis like this, and then open your eyes sometime later, you will not be able to know whether the cylinder has been rotated or not. Okay, just like how we had in the case of sphere. So therefore again we say that the cylinder is symmetric with respect to rotation about the axis shown. Okay, so these two cases were examples wherein the symmetry was continuous. That is, no matter how much we rotate about this axis, it is always going to seem as if it has not been rotated. Okay, but we can also have discrete symmetries. Okay, discrete rotational symmetries. So for this I am going to consider example in 2 dimension. So if I take an equilateral triangle and I rotate it about an axis which passes through the center and perpendicular to this plane, that is to our board, then this will be symmetric only if we rotate it by 120 degrees. Okay, and similarly a square is symmetric if we rotate it by 90 degrees, and similarly a pentagon, something like this, it must be, all sides must be equal, will be symmetric with by rotation by 360 by 5 and so many degrees. And similarly a hexagon, every 60 degree rotation is going to give us the same shape. So these are examples for discrete rotational symmetry. And in 2 dimension, continuous rotational symmetry will be that for a circle. Okay, so these examples must have given you enough intuition on what do we mean by continuous symmetry and discrete symmetry, and when do we say a system is symmetric under a particular operation. Okay, now let us consider a more abstract example, and here we are going to consider a transformation on a particular function. So a more abstract example. So far we had considered only geometric examples. So now we are going to move into some more abstract examples, and before we go into that, let me just state the following. It is possible to think of functions of some variables as symmetric in the sense that if one changes the values of the variables in a certain way, the value of the function is invariant. Okay, so let us understand this statement with an example. Let us consider a function which depends on x and y given by x square plus y square. Okay, now if I perform the transformation from x to some x bar given by x cos theta minus y sin theta for any value of theta, and y to y bar equal to x sin theta plus y cos theta. So under this transformation, you can check that f of xy is going to be equal to f of x bar y bar. Okay, so if you substitute the same value for x and y in this and take any value of theta, you will see that the value of the function remains the same no matter what theta you choose. In a way, this is the abstract formulation of this example, because the equation of a circle is basically x square plus y square is equal to r square, and this is equal to x bar square plus y bar square is basically saying that we are rotating this circle by an angle theta and the value of the radius remains unchanged, or the shape of the circle remains unchanged. Okay, and this is the more abstract formulation of the same thing that we have seen. Okay, so here we say that, therefore we say that f is symmetric under the transformation xy to x bar y bar. Okay, so with that we come back to what we were doing here. So we come back to this part. So now, so we know what symmetry means now. So now, when can we say that a system is symmetric? When can we say that a system is symmetric under some transformation? Okay, this is the question we are trying to answer. So the answer for this is that this is true when there is no change, in the mechanical behavior of the system under this transformation. So what I mean by this is that, just like how when we rotate a circle there is no change in the shape of the circle, similarly for a mechanical system we say that the system is symmetric with respect to some transformation when there is no change in the mechanical behavior of the system under such a transformation. Okay, so how do we define this mechanical behavior? We know that the mechanical behavior, which we have termed very vaguely here, of the system is completely determined by the Hamiltonian. Okay, because we have seen in our previous lectures that a system can be characterized, or the mechanical behavior of a system can be characterized either using the Lagrangian formulation or the Hamiltonian formulation, in which case we need to know what the Lagrangian function is or the Hamiltonian function is respectively. Okay, so it is completely determined by the Hamiltonian of this system, and the Hamiltonian is defined in a given phase space. Okay, so I hope that it is clear. Therefore, invariance of mechanical behavior is same as saying invariance of the Hamiltonian function. Okay, and since H is defined in phase space, the transformation can be defined in phase space as the transformation can be defined in phase space as just a transformation from PQ to some PQ. Okay, and this is exactly what we do in the active interpretation of a canonical transformation. Okay, so this transformation may result in rotation or translation or a combination of both, and so on. Okay, and it can be continuous or discrete. Okay, now it all depends on what this transformation does, whether it rotates the system or translates the system or does both, or whether it is continuous or whether it is discrete, and so on. And if the Hamiltonian is invariant under such a transformation, we say that the system is symmetric under that transformation. Okay, so for example, if this particular transformation is basically the same as saying that we have rotated the system by some angle about some axis, and if the Hamiltonian is invariant, we say that the system is invariant under such a rotation. Okay, and we are going to see some examples of this kind in detail in our next video. Okay, so let me just continue this. So what is the connection here? What is the connection that we have been seeking? We want to connect this symmetry into a quantity that is conserved. Okay, and that is what we are going to do in this final part of the video. Okay, so if H is invariant under the transformation which takes us from point A to point B. So now we are coming to this guy here. We are going from point A to point B via an infinitesimal canonical transformation. So here the picture has been exaggerated. This point A and point B are very close together because it's an infinitesimal canonical transformation. And if our g, which is the generating function of the transformation, is such that it is not explicitly dependent on time, then our change in the Hamiltonian is basically the difference in the value of the Hamiltonian at the point B and A. So here, if we consider that H is invariant under the transformation from A to B, the system must be symmetric under this transformation, because that is how we defined what we mean by symmetry. That is, the mechanical behavior of the system should not change, which in turn means that the H should be invariant, and if H is invariant from A to B, it implies that the system is symmetric under this transformation. Okay, but as we have seen, this is true only if G is conserved, or in other words, dg by dt is equal to 0, and of course we are assuming that dou g by dou t is already 0, or the quantity which is generating this transformation is not explicitly dependent on time. So therefore, if g is a quantity that is conserved, okay, and not explicitly dependent on time, then the system is symmetric with respect to the infinitesimal canonical transformation that is generated by G. Okay, and this is the connection between a quantity that is conserved and the corresponding symmetry of the system under the transformation which is generated by this quantity. Okay, and we can also state the converse of this statement. So conversely, if the system is symmetric under an infinitesimal canonical transformation, then the corresponding function g, which is a part of the generating function, must be conserved. Okay, so this establishes the connection that we have been seeking between a quantity that is conserved and the corresponding symmetry in the system with respect to the transformation generated by such a quantity. Okay, and in next video we are going to see some of the examples of these cases so that we understand this connection better. So thank you for watching. See you next time.